The Kinematical System Laboratory of the Mechanical Engineering School at Tel Aviv University presents Inventing a Mechanical Transistor Using a Multidisciplinary Combinatorial Design Approach.
I would like to show you how this idea works. You see, here we have all the engineering domains. And here we have the mathematical representations, which we call them combinatorial representations. The idea is to transform knowledge device from one domain to another domain. We do not do it directly. We do it through the mathematical models, which are called combinatorial representation. In this talk, we will show only one demonstration, which is we took the mechanical transistor from electronics. We will move it to its mathematical model. From there to another model, and from there to mechanical engineering systems. So we take one device, go it up, and going down to another engineering domain.
Here we will show you the difference between the current configurations of mechanical amplifiers to our new concept of a mechanical transistor. On the left, you see an example of an amplifier that reduced the motion in order to gain force. On the right, the amplifier reduces the force in order to gain velocity. This new device has unique properties not known yet in mechanics. The input and output motion is the same, but there is a change between the input and output forces. These forces are increased or decreased. On the bottom left, we can see that the output force is much greater than the input force, but the velocity remains the same. On the bottom right, we see that the input force is much greater than the output force, and again, the velocity remains the same. In this video, we'll see a device that demonstrates the mechanical transistor. This device was built in our laboratory. Using the device enables one to lift himself and go up with the same velocity that he pulls the rope. The output force that comes out from the device is much greater than the force he applies. In fact, it is multiplied and increased by beta.
Let us look at the schematic description of this transistor. You can see we have input voltage and input current. It amplifies only the current. If we look at the schematic description of the mechanical transistor, we have the same idea. The input velocity remains the same as the output velocity, while the input force is multiplied by the amplified ratio beta, which appears here.
Do we have such a device in mechanics? We search for a device whose function is to increase the output force beta times in relation to the input force and keep the output velocity similar to the input velocity. Very strange, but apparently we don't have such a device in mechanics.
So we are now ready to see what came out from the transformation. We have the transistor, we moved it up, then through the representation, and now we can see this is a mechanical transistor. We are happy to introduce it. This is equivalent to the electronic transistor, and we can see that it has the same topology and the same behavior. We can see here the mechanical transistor and the electronic transistor. Topology is the same, 3 elements. Here we have the base, here we have the link base. Here we have the connector, here we have the connector. Here we have the emitter, here we have the emitter. Now the behavior is the same. The input velocity is almost the same as the output velocity, the rotation of the emitter link. Now the force in the input shaft, in the base, is multiplied by beta, and we derive the force outside in the emitter, like we have here. So doing the transformation, we derived a device that it is equivalent or isomorphic to the device in electronics. Now let us observe the special phenomenon in this device. You see that, for example, if now here I have 2 watt, the input power is 2, the output power here is 200. So there is missing energy of 198. So this device has to take 198 watt from the collector. So the emitter goes and asks for this specific amount of energy from the collector.
The amplifier ratio in this device is 70. Therefore, the pull force applied on the cable is multiplied by 70. It is easy to see that the enhanced force lifts the chair easily and enables to lift 100 kilograms or 220 pounds with the force of just 2 fingers. The difference of energy is supplied by the collector wheel without any electronic control system.
So the behavior is like this. The emitter goes to the right, takes the needed energy. Now it takes it, and it knows through the friction, and I will not talk about it now, how it does the exact amount of energy it takes. After it takes it, and it goes left. Then it needs another energy, it goes to the right, then to the left. It's like a dance. Left, right, left, right. All this without any electronic control system.
This work is a part of a more general project called the Knowledge Engineering Genome that is done with Professor Reich. In the project, we try to classify and sort all of the devices into domains and relate to them as genes. A future practical application of the mechanical transistor can be used in operating rooms. Any small change in the patient is amplified, and the surgeon feels it strongly.
In short, I tried in this movie to show you how we did develop devices and how we are expected to develop more devices. How we do it? We go to one of the engineering domain, let us go to the representation, move between the representation, and then goes down to another engineering domain. And here we come with another new novel device. More detail I will give you in my talk. Thank you.